Right now, a record stands that took more than half a century to break. On April 6th, 2026, 4 human beings traveled further from Earth than any person in history. Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen aboard NASA's Orion spacecraft crossed a threshold that had remained untouched since the final days of the Apollo program. They traveled 25,2000 miles from home. The moment their distance counter surpassed the record set by the battered crew of Apollo 13 inches, April of 1970 mission control erupted. Wiseman's voice, steady and clear through the communication link, carried the weight of every astronaut, every engineer, every dreamer who had spent the intervening decades waiting for this moment to arrive. He spoke of the generations that would follow. He spoke of records meant to be broken. The world watched, and for a brief and luminous moment, it felt like humanity had taken a genuine step toward the stars. But here is what that celebration quietly concealed. 25,2000 miles sounds like a number that should mean something, and by any measure a human body can feel it does. If you attempted to drive that distance in a car, maintaining highway speeds without stopping, without sleeping, without ever pulling over for fuel, the journey would consume roughly 5 months of your life. That number exceeds the total distance most people travel across their entire lifetimes, multiplied by a factor of 100. The engineering required to place 4 human beings at that distance from Earth alive, functional, and capable of returning safely represents one of the most demanding technical achievements our civilization has ever produced. The courage required to sit atop a rocket and accept that destination is a different category of human experience entirely. And yet, Mars, the very next destination on humanity's list, the closest planet we have ever seriously considered, sending people to orbits the Sun at an average distance of roughly 140 million miles from Earth. That number fluctuates depending on where both planets sit in their orbits around the Sun. At its closest approach, Mars can come within approximately 34 million miles. At its farthest, the gap stretches to 250 million miles. A realistic crewed mission would likely launch during a favorable alignment window and cross somewhere between 30 and 60 million miles of interplanetary space to reach the planet. Take the most optimistic figure, and 34 million miles, the absolute minimum distance to Mars under the most favorable possible orbital geometry. The record-breaking distance of Artemis 2, the farthest any human being has ever traveled from Earth, represents less than 1% of that figure. Less than 0.8% to be precise. To reach Mars at its closest approach, you would need to multiply the greatest distance any human has ever achieved by more than 134. 134 times farther than the farthest we have ever gone. And Mars is not far. Mars is our next-door neighbor. Mars is the nearest plausible destination for a crewed mission beyond the Moon. It is the easiest interplanetary target available to us, the one with the thinnest atmosphere, the most manageable surface conditions, the most accessible water ice, the day length closest to our own. If the greatest human journey in history registers as less than 1% of the trip to our most forgiving neighboring planet, then the honest answer to how far humans could ever travel begins to look very different from what most people allow themselves to imagine. This is not a story about what we hope to do. It is not a story about what science fiction has promised, or what optimistic timelines have suggested, or what the most enthusiastic voices in aerospace claim is just around the corner. This is a story about what physics, biology, energy, and the brute arithmetic of distance will actually permit. And the answer arrived at, honestly, is closer and more final than the culture of human space exploration has ever been comfortable admitting. If you find yourself drawn to questions like this one, the kind that reframe everything you thought you understood about where we stand in the cosmos, consider hitting that like button and subscribing. It costs nothing, and it genuinely helps this channel continue making these journeys together. Now, find yourself a comfortable place to settle in. Turn down the lights if you like. What follows will take some time, and it is worth every minute of it. Let's begin. To understand where the limit lies, you have to begin at the only place beyond Earth's orbit where human beings have ever actually stood, the Moon. Not as a symbol, not as a memory, but as a precise engineering benchmark. Because the moon tells you something specific and essential about what human space travel requires and what it cannot do without. Between July of 1969 and December of 1972, human beings walked on the lunar surface across 6 Apollo missions. Each mission lasted between 8 and 12 days, from launch to splashdown. The longest surface stay achieved by the crew of Apollo 17 lasted approximately 3 days. The astronauts carried everything they needed for the duration. There was no resupply. There were no deliveries. Everything that sustained them had been loaded aboard in Florida before the rocket left the ground, and the margin between what they carried and what they needed was terrifyingly thin. But the moon possessed one characteristic that made every other challenge manageable. It was close. At an average distance of roughly 2,400,000 miles, the moon sits close enough to Earth that light covers the distance in approximately 1.3 seconds. A radio signal takes the same time. When an astronaut spoke from the lunar surface, the words reached mission control in Houston before the speaker had finished drawing the breath that produced them. When a question was asked from Earth, the answer could arrive within 3 seconds. Communication was not instant, but it was close enough to feel that way. It preserved the psychological reality of connection. The crew was far from home by any human standard, but they were not alone in any absolute sense. Earth was there on the other end of the radio, present and responsive and near. More critically, the moon was close enough to return from. Apollo 13 demonstrated this with brutal clarity. On April 13, 1970, an oxygen tank in the service module exploded 20,000 miles from Earth, crippling the spacecraft and eliminating the planned lunar landing. The crew had no good options. What they had was proximity. Earth was 2.5 days away. Commander Jim Lovell, Jack Swigert, and Fred Hayes used the lunar module as a lifeboat, swung around the far side of the moon to use its gravity as a slingshot, and aimed themselves back at Earth. They nearly died. The carbon dioxide scrubbers were failing. The temperature inside the spacecraft dropped to near freezing. They rationed water to less than 6 ounces per person per day. The re-entry calculations had to be performed manually when the guidance computers were powered down to conserve electricity. They survived because Earth was 2.5 days away. That proximity is the invisible foundation beneath every successful element of the Apollo program. It is the reason abort options existed at nearly every mission phase. It is the reason a replacement guidance computer could be improvised from pen and paper calculations in time to matter. It is the reason 12 men could walk on an alien world and return alive despite hardware failures, navigation challenges, and the unrelenting hostility of an environment that every biological instinct screams is wrong. Now watch what happens when you extend that logic to Mars. A crewed mission to Mars using current or near-future propulsion technology would require between 6 and 9 months of transit in each direction. The precise duration depends on the trajectory selected and the planetary alignment at the time of launch. Most serious mission architectures employ what engineers call a Hohmann transfer orbit, or a modified version of it. This is the most fuel-efficient path between 2 planets, one that uses the geometry of orbital mechanics to minimize the energy required for the journey. The cost of that efficiency is time. A crew launching on a minimum energy trajectory during a favorable alignment window would spend approximately 7 months coasting through interplanetary space before reaching Mars orbit. Not 7 hours, not 7 days, 7 months in a sealed vessel crossing a void where every resource the crew needs must come from what they carried aboard, and where every problem they encounter must be solved with what they have on hand. 7 months to arrive, and then the waiting begins. Once a crew reaches Mars, they cannot simply turn around and come home. The planets move. The orbital geometry that allowed them to make the trip changes continuously, and the next window favorable for a return journey does not open for approximately 500 days. 500 days. That is the surface stay built into virtually every proposed Mars mission architecture. Not because mission designers want to keep people there that long, but because the physics of planetary orbits leaves no alternative. The crew must remain at Mars for roughly a year and a half on a world with a surface temperature averaging negative 80 degrees Fahrenheit, an atmosphere 95% carbon dioxide and less than 1% as dense as Earth's, no liquid water on the surface, and no breathable air anywhere. Add the transit times: 7 months out, 500 days at Mars, 7 months back. The total mission duration approaches 1,000 days, nearly 3 years. 3 years is not an extended expedition. 3 years is long enough for a child born at the moment of launch to be walking and talking by the time the crew returns. 3 years is the time required to complete most graduate degree programs. 3 years confined inside a spacecraft and a surface habitat, with a small crew separated from every other human being by tens of millions of miles of vacuum, with no possibility of rescue if something goes wrong. And something will go wrong. The communication delay between Earth and Mars ranges from approximately 4 minutes at closest approach to roughly 22 minutes at maximum separation. A round-trip exchange, a question sent and an answer received, takes a minimum of 8 minutes and can extend to nearly 45. Real-time conversation is impossible. If a crew member develops a medical emergency on Mars, they cannot call a doctor and receive instructions in time for those instructions to help. By the time a description of the symptoms reaches Earth and a response travels back, the situation will have resolved itself one way or another without external input. Every diagnosis, every procedure, every decision made under pressure must be made by the crew alone with whatever knowledge and equipment they brought from Earth, with no one to call and no one who can reach them. This is qualitatively different from the Moon. On a lunar mission, Earth is never more than 1.3 seconds away, in the only sense that matters when lives are at stake. On Mars, Earth is a voice on a delay so long it cannot function as guidance in any real emergency. The crew is operationally, medically, and psychologically on their own, in a way that no humans who have ever attempted space travel have experienced. Radiation transforms this isolation from difficult to potentially catastrophic. Beyond the protection of Earth's magnetic field in the open space between planets, a crew is exposed to 2 primary sources of ionizing radiation. The first is solar energetic particles, high-energy protons expelled during solar flares and coronal mass ejections, which arrive with little warning and can deliver dangerous doses in hours. The second is galactic cosmic rays, extremely high-energy particles originating from sources outside the solar system, from supernova remnants and other violent astrophysical events scattered across the galaxy. These particles travel at velocities approaching the speed of light and carry energies far exceeding anything a solar flare produces. Galactic cosmic rays are the more insidious threat. They include heavy ions, particles with large atomic nuclei, sometimes called HZE particles, which can penetrate centimeters of solid shielding material and cause severe direct damage to DNA. They do not merely increase cancer risk in the statistical sense that smoking increases cancer risk. They physically shatter chromosomes, damage neurons, and alter cellular function in ways that accumulate continuously throughout the mission. NASA's Mars Science Laboratory measured the radiation environment during its transit from Earth to Mars between 2011 and 2012. The round-trip dose for a human crew following the same trajectory came out to approximately 0.66 sieverts. NASA's current career exposure limit for astronauts, updated in 2022, is 0.6 sieverts across an entire career regardless of age or sex. A single Mars transit before the crew has set foot on the surface or begun the return journey would already exceed the total radiation budget NASA considers acceptable for a lifetime of space work. Add the surface stay where Mars's thin atmosphere and absent magnetic field provide only partial shielding, and the total mission dose pushes well beyond any threshold associated with acceptable risk. The health consequences are not abstract. Elevated radiation exposure increases the lifetime risk of cancer across multiple organ systems. It accelerates cardiovascular disease. It causes measurable damage to the central nervous system, including changes to cognition, memory, and emotional regulation that animal studies suggest may be permanent. A Mars astronaut would almost certainly be limited to a single interplanetary mission in their career, And even that single mission carries a measurably shortened life expectancy on the other side of it. Shielding can reduce the dose, but galactic cosmic rays are so energetic that even substantial thicknesses of aluminum or polyethylene offer only partial protection. Worse, when heavy ions strike metal shielding, they produce secondary radiation, a cascade of lighter particles that scatter in all directions inside the spacecraft. Poorly designed shielding can actually increase the dose received by the crew. Water and hydrogen-rich materials perform better than metals, but they add mass to the spacecraft, and mass is the variable that controls everything. Every kilogram a crew needs for a 3-year mission must be launched from Earth's surface against the full force of gravity, accelerated to interplanetary velocities, decelerated at Mars, and potentially launched again for the return trip. Food for the crew across 1,000 days. Water, even with the most efficient recycling systems yet devised, which recover approximately 90% of moisture from urine respiration and sweat, but never reach 100%. Oxygen. Medical supplies for every condition that might develop in 6 people over 3 years. Spare parts for every critical system. Radiation shielding. Exercise equipment, because without it, the crew's bones and muscles will degrade to a degree that compromises their ability to function. Scientific instruments, tools for surface operations. The total mass for a crewed Mars mission under most serious proposed architectures runs into the hundreds of metric tons. Launching that mass from Earth's surface requires either an enormous vehicle or a series of cargo missions sent ahead to pre-position supplies and equipment at Mars before the crew ever leaves. The pre-positioning approach is the more practical of the two, which tells you something about how impractical the single launch approach is. But pre-positioning introduces its own category of risk. Cargo missions to Mars must be launched during the favorable alignment window that occurs roughly every 26 months, arriving before the crew departs. If a cargo mission fails, there is no quick replacement. The next launch opportunity is more than 2 years away. A crew arriving at Mars to find their habitat damaged, their return vehicle non-functional, or their food supply compromised faces, a situation for which no contingency plan can provide a meaningful response. They cannot call for help. They cannot wait for a resupply. They are there. This is the first critical insight. The difficulty of crewed space travel does not increase gradually and proportionally with distance. It escalates in lurching, compounding leaps. Each successive destination is not merely farther in miles, it is harder in every dimension that sustains human life. And the gap between Mars, the easiest interplanetary target, and everything beyond it is not a gentle slope, it is a cliff. Consider what lies past Mars, not in the abstract sense of pointing at a star chart and naming destinations. In the concrete physical sense of asking what it would actually require to place a human being at those distances and return them alive. Because the moment you extend the analysis beyond the red planet, the mathematics of human survival does not merely become more difficult, it changes category entirely. The asteroid belt stretches from roughly 2 to 3.5 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. Jupiter orbits at 5.2 astronomical units, Saturn at 9.5, Uranus at just over 19, Neptune at 30. Each successive destination is not simply farther in miles, it is harder in every dimension that determines whether a human crew can survive the journey and return. Travel time lengthens from months to years to decades. Communication delay grows from minutes to hours. Solar energy diminishes with the square of the distance from the Sun, making power generation increasingly difficult. The possibility of resupply, already effectively zero at Mars, does not merely stay at zero as you move outward. It becomes a concept so remote from operational reality that mission planners stop including it in their calculations at all. Jupiter is the first destination past Mars that anyone with serious interplanetary ambitions would consider. It is also the destination where the mathematics of human space travel begins to collapse under its own weight. Jupiter orbits the Sun at an average distance of roughly 484 million miles from Earth. Under the most favorable planetary alignments, using a transfer trajectory, similar to what a crewed Mars mission would employ, the transit time to Jupiter stretches to approximately 2 years and 9 months. Not 2 years and 9 months for the full mission. 2 years and 9 months just to get there. The return trip takes equally long, and unlike Mars, there is no solid surface waiting at the end of the journey. Jupiter is a gas giant. Its visible surface, the swirling amber and cream bands that make it one of the most recognizable objects in the solar system, is not terrain. It is the uppermost layer of an atmosphere that descends thousands of miles into increasing pressure and temperature until it transitions into a sea of liquid metallic hydrogen under pressures millions of times greater than the surface of Earth. There is no ground. There is no landing site. There is nowhere to stand. A crewed mission to Jupiter would be an orbital mission. A crew circling a planet they could never touch, staring into cloud formations large enough to swallow Earth whole with no surface to work on, and no reason to be there that a robotic probe could not serve more efficiently at a fraction of the cost and none of the biological risk. But the transit time is not the primary obstacle. The primary obstacle is what Jupiter's environment does to everything that enters its domain. Jupiter possesses the most powerful planetary magnetic field in the solar system. Its magnetic dipole moment is approximately 20000 times greater than Earth's, generating a magnetosphere so vast it extends millions of miles into space in every direction. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear larger than the full moon in our sky, and within that magnetosphere, trapped in its invisible architecture, are radiation belts of an intensity that reduces every calculation about human space travel to rubble. The innermost radiation belts surrounding Jupiter are among the most hostile environments in the solar system. An unshielded human being entering those belts would receive a lethal radiation dose in a matter of minutes, not hours, minutes. Even at the orbital distances of Jupiter's larger moons, the radiation environment vastly exceeds anything encountered during interplanetary transit. The Van Allen belts surrounding Earth, the radiation zones that Apollo crews pass through on their way to the moon, are gentle by comparison. Passing through Earth's radiation belts took the Apollo crews less than 30 minutes, moving quickly enough that the total dose was manageable. Jupiter's radiation belts extend across distances that would require days or weeks of transit, delivering doses that no amount of conventional shielding can reduce to survivable levels. NASA's Juno spacecraft, which has been orbiting Jupiter since July of 2016, was built specifically to survive this environment. Its most sensitive electronics are enclosed inside a titanium radiation vault, with walls approximately 1/3 of an inch thick, weighing around 400 pounds. The entire spacecraft was designed from the ground up with radiation tolerance as a primary engineering requirement, not an afterthought. Mission planners placed Juno on highly elliptical orbits that minimize the time spent in the most intense radiation zones, swooping quickly through the inner regions and spending most of the mission at safer distances. Even with all of this, Juno's instruments have accumulated significant radiation damage over the course of the mission. Systems have degraded. Components have been affected in ways that required mission controllers to adapt their operations. Juno carries no crew. It requires no life support. It has no food, no water, no oxygen, no medical supplies, no psychological support systems, no exercise equipment. It is a machine designed to endure what no human body could withstand. And even it takes damage. This is the reality of Jupiter, not the planet of beautiful images and scientific wonder, though it is both of those things. The planet whose radiation environment treats the most hardened spacecraft ever sent there as a temporary tolerance rather than a permanent resident. But the conversation about Jupiter never stays at Jupiter itself. It always migrates to the moons. And this migration is worth examining carefully, because the moons of Jupiter are where scientific possibility and human impossibility intersect most sharply. Europa is Jupiter's 4th largest moon, slightly smaller than Earth's moon, covered in a shell of water ice that radar measurements and gravitational analysis suggest conceals a liquid water ocean roughly 60 to 150 miles deep. Tidal heating from Jupiter's gravitational pull flexes the moon's interior, continuously generating the energy that keeps that ocean liquid despite surface temperatures that average -260 degrees Fahrenheit. Where there is liquid water and an energy source, the chemistry that produces life becomes possible. This is the reason Europa has occupied the center of astrobiology discussions for decades, not because we know life is there, but because the conditions that permitted life to emerge on Earth may be present beneath that ice. The surface radiation dose on Europa is approximately 540 rem per day. A lethal radiation dose for a human being delivered over a short period is roughly 400 rem. An astronaut standing on Europa's surface in a standard spacesuit would receive a fatal dose of radiation within 24 hours, not within a week, within a day. The same Jovian radiation belts that threaten any spacecraft approaching Jupiter bathe Europa's surface continuously, bombarding it with high-energy particles that would destroy human biology faster than any other hazard of the outer solar system. Even inside a heavily shielded habitat, the cumulative exposure would build relentlessly. The ice crust itself provides some attenuation, which is why proposals for Europa exploration often involve drilling or melting through the ice to work beneath the surface. But the ice is estimated to be between 10 and 30 kilometers thick, penetrating it in a radiation environment that degrades electronics and structural materials, continuously maintaining a pressurized habitat below the surface, sustaining a crew for the years required to conduct meaningful science with no possibility of resupply or emergency evacuation from Earth. Using technology that does not exist presents a combination of challenges that no serious engineering study has come close to resolving. NASA's Europa Clipper mission, launched in October of 2024, represents the realistic alternative. It will study Europa through dozens of close flybys from the relative safety of Jupiter orbit, using instruments that can analyze the combinatorial and material ejected through cracks in the ice, measure the depth and salinity of the subsurface, ocean, and map the moon's surface in detail. It carries no crew. It requires no life support. It was designed from the beginning to operate in the radiation environment that would kill a human passenger. Europa Clipper will learn more about that moon in its operational lifetime than any crewed mission could hope to achieve at a cost and risk level orders of magnitude lower. This is the pattern that repeats itself throughout the outer solar system. The destinations most interesting to science are precisely the destinations most hostile to human survival. The two qualities are not coincidental. They arise from the same physical conditions: extreme cold, intense radiation, the absence of breathable atmosphere, the presence of chemistries and energy sources that are scientifically significant because they differ so radically from anything found on Earth. The environments that make these worlds scientifically compelling are the same environments that make them biologically lethal. Move outward from Jupiter to Saturn, and the distances nearly double. Saturn orbits the Sun at an average distance of roughly 886 million miles. Even the most efficient trajectory to Saturn requires approximately 6 to 7 years of transit each way. A round-trip crewed mission to Saturn's system with a minimal operational stay would last somewhere between 13 and 15 years. 15 years is not a mission duration, it is a life chapter. An astronaut who departs for Saturn at age 35 returns, if everything goes perfectly, at age 50. Their children, young when they left, would be approaching adulthood. Their parents might have died in their absence. The world they return to would have changed through 15 years of technological development, political shifts, cultural evolution, and personal history they experienced only as time-delayed messages received months after the events they described. They would be strangers to their own lives in ways that no amount of preparation or psychological training can fully address, because nothing in human experience prepares a person for a 15-year absence from everyone and everything they have ever known. And this assumes the mission succeeds completely, without catastrophic failure, without a single life support component failing beyond the crew's ability to repair it. The International Space Station, the most sophisticated long-duration habitat humanity has ever built, requires resupply missions from Earth roughly every few months. It receives regular deliveries of food, water replacement parts, experimental equipment, and critical hardware components. Its life support systems experience frequent maintenance issues. Carbon dioxide scrubbers require servicing. Water recycling units malfunction and require repair. Oxygen generation systems develop faults. These issues are managed, addressed, and resolved because resupply is never more than a few weeks away. and because the engineering expertise of thousands of ground controllers is always available in near real time. On a mission to Saturn, resupply does not exist. Every component failure must be addressed with the tools and spare parts aboard the spacecraft. Every technical challenge must be solved by the crew alone, using whatever knowledge they brought with them. Every part that wears out is gone permanently. The mission carries no margin for the ordinary entropy that slowly degrades complex machinery over years of operation, because there is no way to replenish what is consumed or replace what breaks beyond repair. No closed-loop life support system has ever been demonstrated to function reliably for 15 years without resupply or major external maintenance. The longest continuous human occupation of a space habitat is the International Space Station, and it has never operated without regular resupply. The longest sealed ecological experiments conducted on Earth, including the biosphere, 2 projects in Arizona in the early 1990s, failed within months to maintain the atmospheric and biological balances required to sustain their inhabitants without external intervention. Biosphere, 2 experienced significant oxygen depletion species die-offs and agricultural failures within its first 2 years. It was not in space, it was in the Arizona desert, with the full resources of Earth's industrial civilization available to its operators within driving distance, and it still failed to sustain itself. A spacecraft carrying humans to Saturn would need to be what Biosphere 2 could not be, a perfectly self-sustaining enclosed ecosystem operating without failure for a decade and a half, in an environment of continuous radiation, bombardment, mechanical stress, and the gradual accumulation of every small error and unforeseen interaction that complex systems inevitably generate over time. Enceladus is a moon of Saturn that has captured scientific attention with unusual intensity since the Cassini spacecraft flew through geysers erupting from its south polar region. These plumes shoot water, vapor, ice particles, and complex organic molecules hundreds of kilometers into space. Cassini detected molecular hydrogen silica nanoparticles and compounds consistent with hydrothermal activity on the ocean floor beneath the moon's icy surface. The combination of liquid water, chemical energy from hydrothermal vents, and complex organic chemistry represents the set of conditions that produced life on Earth. Enceladus may be the single most promising target in the solar system for finding evidence of extraterrestrial microbial life. It orbits Saturn, nearly 1 billion miles from Earth. The radiation environment around Saturn is less severe than Jupiter's, but the transit time and logistical demands compound every challenge already identified for a Jovian mission. A crewed mission to Enceladus would face the same radiation exposure during transit, the same years of isolation, the same closed-loop life support requirements, the same impossibility of resupply, the same medical autonomy demands, all multiplied by additional years of travel and greater distance from any assistance. Titan, Saturn's largest moon, presents perhaps the most seductive vision of outer solar system exploration. It is the only moon in the solar system with a dense atmosphere thick enough to scatter sunlight into an orange haze. Its surface pressure is approximately 50% higher than Earth's at sea level. Its atmosphere is primarily nitrogen, the same dominant gas that fills Earth's skies. Liquid methane and ethane flow across its surface in rivers and collect in lakes, creating landscapes that look hauntingly familiar in radar imagery while being constructed from chemistry that has nothing to do with water. In some respects, Titan is the most hospitable world in the outer solar system. The dense atmosphere provides natural radiation shielding. A human being on Titan's surface could theoretically walk outside in a heated suit with a breathing apparatus rather than the full pressure suit required on the airless surfaces of the Moon or Mars. The atmospheric pressure means habitats would not need to maintain extreme pressure differentials against a hard vacuum. But Titan's surface temperature averages -290 degrees Fahrenheit. Maintaining a habitat compatible with human survival in an environment nearly 300 degrees below the freezing point of water requires enormous and continuous energy expenditure. At Saturn's distance from the Sun, solar energy is approximately 100 times weaker than at Earth's orbit. Solar panels are functionally useless. Nuclear power is the only viable option, and the reactor's fuel assembly's shielding and backup systems required for a 15-year mission would add tens of thousands of kilograms to an already impossibly massive spacecraft. NASA's Dragonfly mission, a rotorcraft lander approved for flight, is scheduled to arrive at Titan in the mid-2030s. It will fly between sites across the Moon's surface, sampling the chemical composition of Titan's organic-rich environment, searching for evidence of prebiotic chemistry or biosignatures. It carries no crew. It weighs less than 500 kilograms. It requires no food, no water, no breathable atmosphere, no radiation shielding for biological passengers. It is the correct tool for the job, not because human curiosity about Titan is insufficient, but because the physics of the journey makes human passengers the wrong choice for this destination at this moment in our technological development. This distinction deserves to be stated plainly because it is often blurred in popular discussions of space exploration in ways that create a false impression of progress. Robotic exploration of the outer solar system is not a stepping stone toward crewed exploration of the same destinations. It is, in most cases, the permanent solution, not a temporary substitute, while humanity develops the technology to send people, but the optimal approach for these particular destinations given the physical constraints that govern the relationship between distance, time, biological survival, and energy. A robotic probe does not eat. It does not breathe. It does not develop bone loss from prolonged weightlessness or kidney stones from elevated calcium in the blood or vision impairment from fluid shifts in microgravity or depression from years of isolation in a sealed metal environment. It does not require exercise equipment or privacy or psychological support systems or entertainment or the thousands of small inputs that human beings require simply to remain functional across time. It can be powered by a radioisotope thermoelectric generator that produces electricity from the decay of plutonium-238 for decades without refueling. It can enter low-power hibernation modes during transit and reactivate upon arrival. It can tolerate radiation levels that would kill a human crew before they reached Jupiter's orbit. A robot is the ideal deep space explorer. Everything that makes deep space exploration difficult for machines is irrelevant, and everything that makes it impossible for human beings is simply not a factor. Human beings are the opposite. Every advantage robots carry, humans lack. Every constraint that robots ignore, humans cannot escape. The mass of a robotic probe is measured in hundreds of kilograms. The mass of a crewed spacecraft with life support, radiation shielding, consumables, habitation, volume, exercise, equipment, and return capability is measured in hundreds of thousands of kilograms. The fuel required to send a robotic probe to Jupiter is a small fraction of the fuel required to send a crewed vessel on the same trajectory. Not because the distance is different, because the mass is orders of magnitude greater. And in space, mass is the variable that determines cost, complexity, risk, and ultimately feasibility. This asymmetry is the reason humanity has explored the entire solar system robotically and has sent no human being farther than the Moon. It is not a failure of ambition. It is not a failure of funding, though funding is always a constraint. It is a statement about the physical relationship between what human biology requires and what the outer solar system demands. Those two things are fundamentally incompatible in ways that no foreseeable technology resolves. Beyond Saturn, the incompatibility becomes so severe that the concept of a crewed mission begins to lose coherent meaning. Uranus orbits the Sun at roughly 1.8 billion miles, Neptune at approximately 2.8 billion. Transit times to Uranus using chemical or nuclear thermal propulsion stretch beyond a decade each way. A round-trip crewed mission to Neptune would last approximately 30 years. An astronaut who launched at 30 would return at 60. Having spent their entire productive adult life in transit if they returned at all. The radiation exposure accumulated across 30 years in deep space, beyond the protection of any planetary magnetic field, would far exceed any limit associated with long-term human health. The cumulative dose from galactic cosmic rays alone at typical interplanetary flux levels would reach several sieverts, well into the range where health consequences are not elevated risks but expected outcomes. The cardiovascular damage would be measurable. The central nervous system effects, based on animal studies of prolonged HZE particle exposure, would likely include cognitive changes that compromise the crew's ability to perform the mission tasks they were sent to accomplish. No closed-loop life support system has been demonstrated to function reliably for 30 years. No human psychological study has characterized what 3 decades of confinement in a small vessel with a small group of people does to the mind over that duration. The Mars 500 experiment in Moscow, which confined small crews in simulated spacecraft habitats for up to 520 days, documented significant depression, sleep disruption, and cognitive decline within less than 2 years. 30 years is not a scaling of that challenge. It is a different category of problem for which no data exists and no framework for managing it has been developed. Voyager 2 flew past Uranus in January of 1986, 9 years after launch. It reached Neptune in August of 1989, 12 years after leaving Earth. It accomplished this by carrying no crew, no life support, no food, no water, and no psychological support systems. It required no exercise equipment because it has no muscles to lose. It accumulated no cancer risk because it has no cells to irradiate. It did not experience depression, interpersonal conflict, or existential despair about the length of its journey. It simply flew powered by the momentum of its launch and the gravitational assists it received from each planet it passed, sending back data through a radio link that took hours to bridge the distance to Earth. That is the honest comparison, not between what we have built and what we could theoretically build with better technology, between what a machine can endure and what a human body can survive. The gap between those two things is the wall, not a wall made of any particular material, but a wall made of biological reality, made of the fact that human beings are approximately 37 trillion cells organized into systems that require constant specific inputs to continue functioning, and that interstellar distances are not compatible with providing those inputs across the timescales the distances demand. The outer solar system will be explored. It is being explored now through instruments launched years and decades ago, returning data that reshapes our understanding of the solar system's history and composition. Future robotic missions will descend through the atmosphere of Titan, drill through the ice of Europa, sample the plumes of Enceladus, and map the ring systems of Uranus and Neptune in detail that current observations cannot achieve. Those missions will be extraordinary scientific achievements. They will almost certainly reveal surprises that challenge existing models and open new questions that future missions will pursue. But human beings will not follow. Not to Jupiter, not to Saturn, not to Uranus or Neptune. Not because we lack the will, and not because the scientific questions are unworthy of human attention, because the physics does not accommodate human passengers at these distances and durations, because the distances are too great, the transit times too long, the radiation too severe, the logistical demands too extreme, and the margin for error too narrow, because every one of these problems compounds the others, and every proposed solution to one creates new versions of the rest. The outer planets are not destinations waiting to be conquered by the next generation of explorers. They are walls built not from rock or energy fields, but from time, distance, radiation, and the remorseless arithmetic of what it costs to keep a human being alive in an environment that was never configured to support biological life of any kind. Beyond those walls lies a boundary that carries a different weight entirely. It is the boundary that separates the sun's direct influence from the space between the stars. 2 of our machines have already crossed it. They crossed it decades ago. They are still crossing it now, still transmitting faint signals back to Earth from distances so great that the signals take nearly a full day to arrive. No human being will ever stand where Voyager stands. The reasons for that certainty are what the next part of this journey examines, and they are more absolute than anything encountered so far. The heliosphere is not what most people imagine. There is no visible boundary, no line drawn across space, no wall of light or curtain of energy marking the edge of the sun's territory. What exists is a gradient, a region where the outward pressure of charged particles streaming continuously from the sun, the solar wind weakens until it can no longer push back against the incoming flow of particles from interstellar, Space. The transition is turbulent, complex, and spread across a zone rather than concentrated at a single point. Voyager 1 detected it over the course of months, observing shifts in plasma density, magnetic field orientation, and cosmic ray intensity that collectively indicated it had passed from the heliosphere into the interstellar medium. NASA confirmed the crossing in 2013, placing the actual boundary passage in August of 2012 at a distance of roughly 121 astronomical units from the Sun. Voyager 2 followed in November of 2018, crossing the boundary at approximately 119 astronomical units in a different direction. The two crossings at slightly different distances told scientists something specific about the heliosphere's shape. It is not a perfect sphere. It is compressed on the side, facing the direction of the Sun's motion through the galaxy, and elongated into a tail on the opposite side, pushed and pulled by the pressure of interstellar space into an asymmetric structure that our models had not fully predicted. The crossing of the heliopause was one of the genuine achievements of the space age. For the first time, human-made instruments sampled the interstellar medium, directly measuring its density, temperature, and magnetic properties from inside it, rather than inferring them from a distance. The data revealed a boundary region more complex than expected, with multiple transitional layers and plasma structures that existing models had not anticipated. And Voyager's instruments, designed in the 1970s using technology that would be considered primitive by the standards of a modern wristwatch, were sending back these measurements from a realm no spacecraft had ever entered. But crossing the heliopause did not mean leaving the solar system. This distinction matters enormously, and it is consistently blurred in popular accounts of Voyager's journey. The Sun's gravitational influence extends far beyond the point where its wind gives out. The Oort cloud, the hypothesized shell of trillions of icy bodies that surrounds the solar system at its outermost extent, is believed to stretch from roughly 2000 to as far as 100,000 astronomical units from Sun. Objects in the outer Oort cloud orbit the Sun at distances approaching 2 light-years, nearly halfway to the nearest star. Gravitationally, in the most meaningful sense of what it means to belong to a stellar system, the solar system is vastly larger than the heliosphere, sitting at its center like a small bubble in an enormous ocean. Voyager 1, currently at approximately 172 astronomical units, has crossed the wind boundary. It has entered the interstellar medium in the sense that it moves through gas and particles that originated from other stars rather than from our own, but it remains deep within the Sun's gravitational domain. It will not exit the Oort cloud for roughly 300,000 years. It has been flying for nearly half a century, and it is in the most meaningful gravitational sense still inside the solar system. This is the context in which the question of interstellar travel must be understood. Not as an extension of what we have already done, not as the next step after Mars and the outer planets, but as a problem in a fundamentally different category. One governed by distances that make everything discussed so far seem trivially close by comparison. Proxima Centauri sits 4.24 light-years from Earth. In miles, that translates to approximately 25 trillion. Written as a numeral, the number occupies 13 digits. It is a distance so far beyond the reach of ordinary human intuition that every attempt to visualize it requires analogies that themselves strain comprehension. Consider this one. If you placed a marble on a table to represent the Sun and placed a second marble 4 miles away to represent Proxima Centauri, the Earth would be a grain of sand sitting 1 inch from the first marble. The entire solar system out to the inner edge of the Oort cloud at 2000 astronomical units would fit within a sphere roughly the size of a large room surrounding that first marble. To reach the second marble, you would leave the room, leave the building, walk out into the street, and keep walking for 4 miles. At Voyager's current speed of roughly 38,000 miles per hour, covering the distance to Proxima Centauri would require approximately 730,000 years. Pause with that number for a moment. Not as an abstraction, but as a duration. 730,000 years ago, anatomically modern humans shared the planet with Neanderthals. The last ice age had not yet reached its maximum extent. Agriculture would not be invented for another 6,000,000 years. Writing did not exist. Cities did not exist. The oldest known cave paintings would not be created for another 4,000,000 years. Every civilization that has ever risen and fallen, every empire, every language, every religion, every scientific revolution, every war and peace and discovery in the entirety of recorded human history occupies less than 1/10 of the time that Voyager would need to reach the nearest star at its current velocity. And Voyager is fast. It is among the fastest outbound objects humanity has ever launched. It achieved its speed not through continuous propulsion but through gravitational assists from Jupiter and Saturn, using the planet's gravity as a slingshot to add velocity without burning additional fuel. Since its flyby of Saturn in November of 1980, it has been coasting. No engine burns, no acceleration of any kind, just momentum carrying it outward at 3,800 miles per hour for more than 4 decades. The question then is whether faster is possible, whether some propulsion technology existing or conceivable could reduce that 73,000-year journey to something a human crew might survive. Begin with the most mature option on the table. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, typically liquid hydrogen, to temperatures far higher than any chemical reaction can achieve, and expel it through a nozzle at correspondingly higher velocities. The exhaust velocity of a nuclear thermal rocket is roughly twice that of the best chemical engines. NASA tested nuclear thermal engines under the NERVA program during the 1960s and early 1970s, successfully firing prototype engines on the ground before the program was cancelled as Apollo wound down. Modern interest in the concept has revived. Several studies presented at recent aerospace conferences have examined fission-powered propulsion for deep space missions and found meaningful potential for reducing transit times to the outer planets. But nuclear thermal propulsion does not address the interstellar problem in any meaningful sense. Doubling exhaust velocity roughly halves transit time, which matters enormously for a mission to Jupiter or Saturn and is completely irrelevant on interstellar scales. A nuclear thermal rocket traveling to Proxima Centauri might reduce the journey from 7,300,000 years to perhaps 4,000,000. The crew would still be dead by a margin so vast that the improvement is indistinguishable from no improvement at all. You have exchanged one impossibility for a slightly smaller impossibility. The nearest star remains unreachable. Nuclear electric propulsion achieves higher exhaust velocities by using a reactor to generate electricity that drives ion engines. Ion drives produce very small amounts of thrust, continuously over very long periods, gradually accumulating velocity in a way that chemical rockets cannot match over extended timescales. The Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. The technology is proven, but even the most optimistic projections for advanced nuclear electric systems suggest maximum velocities on the order of a few hundred kilometers per second. At 100 kilometers per second, roughly 3 times Voyager's speed, the transit to Proxima Centauri would take approximately 1,300,000 years. The improvement over chemical propulsion is substantial in percentage terms and irrelevant in absolute terms. The crew is still dead thousands of years before arrival. Fusion propulsion represents a more dramatic leap. Nuclear fusion, the process that powers the Sun and every other star in the universe, releases energy by combining light atomic nuclei into heavier ones. The energy yield per unit mass of fuel is roughly 4 times greater than fission and millions of times greater than chemical combustion. A fusion-powered rocket could theoretically achieve exhaust velocities of several thousand kilometers per second, enabling spacecraft to reach a few percent of the speed of light. At 5% of light speed, the journey to Proxima Centauri would take approximately 85 years. That falls within the outer bound of a human lifespan, if barely. The problem is that controlled nuclear fusion has never been achieved as a practical power source, not on Earth, let alone in a compact, lightweight engine suitable for a spacecraft. Despite decades of research, and hundreds of billions of dollars invested globally, sustained fusion power generation remains a goal, not a technology. The conditions required for fusion temperatures exceeding 100 million degrees Celsius, intense magnetic or inertial confinement, and precise management of a plasma that wants desperately to escape its containment have resisted engineering solutions since the 1950s. Progress has been real. The National Ignition Facility achieved fusion ignition in December of 2022, producing more energy from a fusion reaction than the laser energy delivered to the fuel target. It was a genuine milestone. It was also a single pulse, lasting nanoseconds, producing a tiny net energy gain under conditions that bear no resemblance to a continuous power plant, let alone a rocket engine. If fusion power is eventually mastered on Earth, adapting it into a propulsion system small enough, light enough, and reliable enough for a spacecraft represents a second engineering revolution on top of the first. Experts consulted in a 2024 review of interstellar propulsion challenges estimated that practical fusion drives are at minimum a century away, and noted that this estimate assumes the underlying fusion power problem is solved, which itself remains undemonstrated. Even granting fusion propulsion in its most optimistic form, the 8-5-year transit to Proxima Centauri presents its own category of challenges. A crew departing at 30 would arrive at 115 if they arrived at all. The life support system must function without failure for 85 years. The radiation shielding must hold for 85 years of exposure to galactic cosmic rays at interstellar flux levels. The closed-loop ecological system must sustain a crew for 85 years without resupply, without significant component replacement, without any external input of any kind. No system of any complexity has ever operated without failure or major maintenance for 85 years. Not a power plant, not a submarine, not a building. The oldest continuously operating machines on Earth have required regular maintenance, component replacement, and external support throughout their operational lifetimes. An interstellar spacecraft cannot receive any of that, and the crew must decelerate at the destination. Accelerating to 5% of light speed requires an enormous energy input. Decelerating from 5% of light speed requires an equal energy input, applied in reverse. The spacecraft must either carry fuel for both burns, which dramatically increases its mass, and therefore the energy required for the initial acceleration, or it must use some form of magnetic braking against the interstellar medium, a concept that has been proposed theoretically, but demonstrated nowhere. Antimatter propulsion offers the highest theoretical energy density of any known fuel. When matter meets antimatter, both annihilate, completely converting their entire combined mass into energy, according to Einstein's relationship between mass and the speed of light squared. In principle, antimatter is the perfect fuel. In practice, it faces obstacles so severe that serious propulsion engineers treat it less as a near-term option and more as a thought experiment about ultimate physical limits. The problems begin with production. Antimatter does not exist naturally in any accessible quantity in the observable universe. It must be manufactured in particle accelerators, one particle at a time at energy costs that currently result in a price exceeding $60 trillion per gram. The total quantity of antimatter ever produced by all the particle accelerators on Earth combined, accumulated across decades of operation, is measured in nanograms, less than a billionth of a gram. To propel even a modest spacecraft to a meaningful fraction of light speed would require kilograms of antimatter. Producing that quantity at current efficiency would consume more energy than human civilization has generated across its entire history, not in a year. Across all of recorded time, even if production costs dropped by factors of billions, antimatter presents handling challenges that compound the production problem. It must be stored without ever contacting normal matter, because any contact results in immediate annihilation and a burst of gamma radiation energetic enough to penetrate most shielding materials. Magnetic confinement systems capable of holding anti-hydrogen have been demonstrated at CERN for tiny quantities over short periods. Scaling those systems to hold kilograms of antimatter for decades aboard a spacecraft while the spacecraft accelerates maneuvers and operates in the thermal and radiation environment of interstellar space, is a problem for which no credible engineering pathway exists. The annihilation process itself produces gamma rays so intense that shielding the crew would require massive amounts of material, largely negating the mass advantage that makes antimatter attractive in the first place. Studies have estimated that no more than roughly 40% of the annihilation energy could realistically be captured as directed thrust, with the remainder lost as penetrating radiation that would irradiate everything aboard the spacecraft. Antimatter propulsion is not a technology in development. It is a concept in physics, separated from practical application by engineering chasms that no current research program is close to bridging. This brings us to the one interstellar propulsion concept that has received sustained serious attention, secured significant funding, and attracted scientists of genuine distinction: laser-driven light sails. The principle is elegant in a way that almost nothing else in interstellar propulsion can claim. Build a powerful array of ground-based lasers and direct them at an ultra-thin reflective sail attached to a small spacecraft. The photons from the laser array strike the sail and transfer their momentum to it, gradually accelerating the spacecraft to a significant fraction of light speed. The spacecraft itself carries no fuel. All the propulsive energy comes from the laser array left behind on Earth. This eliminates the tyranny of the rocket equation completely, because the propellant, the photons, never needs to be carried aboard. Breakthrough Starshot, announced in April of 2016 by the physicist Stephen Hawking and the technology investor Yuri Milner, proposed exactly this. The plan called for a 100 gigawatt laser array to accelerate gram-scale spacecraft, each smaller than a postage stamp, to 20% of the speed of light. At that velocity, the tiny probes would reach the Alpha Centauri system in approximately 20 years. They would fly through the system, capturing images and data, and transmit the results back to Earth, using the light sail itself as a communication antenna. The return signal would take about 4 years to arrive. Total mission duration from launch to data reception, roughly 25 years. The concept generated extraordinary excitement. $100 million was pledged for initial research and development. Scientists and engineers from leading institutions around the world were recruited to study the key technical challenges. For a brief period, interstellar travel seemed to have moved from the domain of pure fantasy into the domain of ambitious but conceivable engineering. Then the technical realities presented themselves. Not one challenge, a stack of them, each formidable, individually, collectively forming a barrier that has proven resistant to the combined efforts of some of the world's best engineers. The laser array would need to produce 100 billion watts of coherent, focused power. For context, the total electricity generation capacity of the United States is approximately 1.2 trillion watts. The laser array would consume nearly 10% of that entire capacity during each 10-minute acceleration burn. Building the array itself would require optics several kilometers in diameter assembled and aligned with precision measured in fractions of a wavelength of light. No such optical system exists. Nothing approaching it exists. Atmospheric turbulence would scatter and distort the beam as it passed through the air column above the array, requiring adaptive optics systems capable of correcting millions of distortions per second while tracking a target, accelerating at thousands of times the force of gravity. The sail material would need to withstand 100 billion watts of focused laser energy, without melting, tearing, or deforming, while remaining thin enough to be accelerated by photon pressure to 20% of light speed in under 2 minutes. Researchers at the California Institute of Technology identified silicon nitride as a promising candidate material and made meaningful progress on fabrication techniques, including a result published in 2025 that reduced manufacturing costs by a factor of several thousand using optical lithography methods. Progress. Genuine progress on one of many unsolved problems. Communication from the destination posed perhaps the most stubborn challenge of all. A gram-scale probe at Alpha Centauri, 4 light-years from Earth, transmitting data back, using a sail that doubles as an antenna, would produce a signal of extraordinary faintness at the receiving end. Detecting it would require telescope arrays with collecting areas far larger than anything currently planned or funded. The data rate would be measured in bits per second. Transmitting a single image of a planet in the system could take years. By 2025, the project had quietly stalled. Reporting on the project's status found that only a small fraction of the pledged funding had been distributed, spread across roughly 30 research contracts. Key personnel had moved to other positions. The coordinating structure that had initially given the project coherence had dissolved. No formal announcement was made about the project's future. It existed in a state of indefinite suspension, its prospects described by those who had worked on it as deeply uncertain. Breakthrough Starshot demonstrated something important, though not what its founders had intended. It showed that even the most physically plausible interstellar propulsion concept, the one that sidesteps the rocket equation, entirely faces engineering challenges so fundamental that a well-funded high-profile initiative drawing on the best scientific talent available could not identify a clear path forward within a decade of intensive effort. And Breakthrough Starshot was designed for gram-scale probes, chips weighing less than a paperclip, cameras and communication equipment the size of a fingernail, no life support, no food, no water, no radiation shielding for biological passengers, no habitation volume, nothing that a human being requires to survive. Scaling the light sail concept to carry a human crew is not an engineering challenge, it is a category error. The energy required to accelerate a crewed spacecraft, even a minimal 1 to 20% of light speed using laser propulsion, would exceed the total energy output of human civilization, not for a year, but for centuries. The sail would need to be kilometers across. The laser array would need to be planetary in scale. The deceleration problem at the destination, which laser propulsion cannot address, because the laser array is 4 light-years behind you, remains entirely unsolved. If direct propulsion cannot carry humans to the stars within a human lifespan, what about accepting the journey on its own terms? What about simply building a vessel large enough and robust enough to sustain a human population across centuries? A journey to the nearest star would require, regardless of the speed. The generation ship concept proposes exactly this. Build a self-sustaining habitat, a small enclosed world, and launch it on a multi-century journey to a neighboring star. The crew that departs would not arrive. Their children would not arrive. Their grandchildren might not arrive. The ship would carry a population large enough to maintain genetic diversity and social stability across dozens of generations, each born, raised, and dying aboard the vessel until the final generation arrives at the destination. The concept has populated science fiction for a century. Its engineering requirements are another matter. A generation ship would need to maintain a closed ecological system for centuries without resupply of any kind. No closed ecological system has ever been demonstrated to function for more than a few years. Biosphere 2, the most ambitious closed ecosystem experiment conducted on Earth, sealed 8 researchers inside a 3.14-acre enclosed biosphere in Oracle, Arizona, in September of 1991. Within months, oxygen levels began dropping unexpectedly. Carbon dioxide rose to levels that caused headaches and fatigue in the inhabitants. Several species of pollinating insects died off, threatening the agricultural systems the crew depended on for food. Bacterial populations in the soil consumed organic material faster than anticipated, altering soil chemistry in ways that depressed crop yields. The project required external oxygen injection to keep the crew functional. By the end of the first 2 years, the experiment had demonstrated conclusively that designing a closed ecosystem capable of sustaining human life indefinitely is not merely difficult, but represents a problem of complexity that no engineering approach has yet solved. And Biosphere 2 was on Earth. It had access to sunlight. It was surrounded by the full resources of an industrial civilization within driving distance. Its operators could and did intervene when systems failed. A generation ship has none of these advantages. Whatever the ecological system does, whatever equilibria it finds or fails to find, the crew responds to with whatever knowledge and tools they have aboard. There is no external intervention. There is no correction from outside. The social challenges are at least as formidable as the ecological ones. A generation ship would need to sustain a functioning, technically competent society across centuries without the external pressures, resources, and feedback mechanisms that stabilize societies on Earth. Governments would need to persist without the external checks that Earth-based political systems rely on. Educational systems would need to transmit not just cultural knowledge but highly specialized technical expertise, the knowledge required to maintain the ship's systems across dozens of generations without degradation or loss. The crew of Generation 100 would need to understand systems designed and built by the crew of Generation 1, maintained and modified by every generation in between, documented in records that may have been copied, recopied, and reinterpreted countless times. History offers no examples of a technical tradition sustained across 100 generations without significant loss or transformation. The knowledge required to build a Roman aqueduct was largely lost within a few centuries of Rome's decline. The astronomical precision of ancient megalithic cultures disappeared with those cultures. Technical knowledge is fragile across time in ways that enthusiastic projections about generation ships consistently underestimate. The psychological burden on every individual born into the ship would be without precedent in human experience. To be born inside a vessel, to know that you will die inside it, to know that your children will die inside it, and their children after them, for generations beyond your ability to count, to know that the sky you will never see exists somewhere beyond walls you will never pass through, to know that this condition is not a circumstance, but a permanent, inescapable feature of your existence and the existence of everyone you will ever know. No human society has ever been asked to carry that weight. We do not know what it produces across centuries, because nothing in human experience provides data. The Mars 500 experiment, which confined small crews in simulated spacecraft for up to 520 days, documented significant psychological deterioration within less than 2 years. A generation ship's psychological demands would span not 520 days, but thousands of years, imposed not on volunteers who chose the experiment, but on generations of people who had no choice in the matter at all. Suspended animation is the solution most frequently invoked to dissolve these problems. If the crew could be placed in a state of biological suspension for the duration of the journey, the challenges of food, water, oxygen, psychological stress, generational continuity, and social stability would be dramatically reduced or eliminated. The crew would sleep through the centuries and awaken at the destination biologically unchanged, carrying the full technical knowledge they possessed at departure. The difficulty is fundamental. Suspended animation for human beings does not exist. It has never been demonstrated. No pathway from current biological science to reliable whole-body human cryopreservation has been identified. Cryopreservation of individual cells is possible. Cryopreservation of small tissue samples is practiced in medicine. Cryopreservation of whole organs remains an active research challenge, with success demonstrated for some organ types but not others. Cryopreservation of an entire human body, maintaining cellular integrity across all tissues, simultaneously preventing ice crystal formation that ruptures cell membranes, managing the biochemical cascades that occur during freezing, thawing in a system of 37 trillion interdependent cells, and reversing the entire process to restore full biological function across every organ system, is so far beyond current capability that it sits in the category of speculation rather than theoretical science. We do not know if it is possible. We do not know if it is impossible. We lack the scientific understanding of biology at the required level of precision to determine which. Time dilation offers the final possibility that physics itself presents, and it is the one that requires the least speculation. Einstein's special theory of relativity, confirmed experimentally with precision across more than a century of testing, predicts that time passes more slowly for objects moving at velocities approaching the speed of light. A spacecraft traveling at 90% of light speed would experience time at approximately 44% of the rate experienced by observers at rest. For the crew, A journey that took 10 years by Earth's clocks would feel like only about 4.5 years of subjective experience. At 99% of light speed, the dilation becomes extreme. The 4.24 light-year journey to Proxima Centauri measured by Earth clocks would feel like only about 7 months to the crew. This is not speculation. Time dilation has been confirmed experimentally with atomic clocks carried aboard aircraft and satellites, and with observations of fast-moving subatomic particles that decay more slowly when moving at high velocities than when at Farthest. It is measured fact. It means that in principle, a crew traveling fast enough could experience the journey to a nearby star within a subjective human lifetime. The problem, as always, is achieving the required speed. Accelerating a crewed spacecraft to 90% of light speed requires an energy input of staggering magnitude. The kinetic energy of a 1,000-ton spacecraft at 90% of light speed is roughly equivalent to 200 years of humanity's total energy consumption across all sources combined. Coal, oil, gas, nuclear, solar, wind, everything our civilization produces and consumes for 2 centuries. Producing, storing, and converting that energy into directed thrust is a challenge that no known or proposed technology can address within any plausible engineering framework. And the spacecraft must decelerate at the destination, an equal energy expenditure in reverse. The total energy budget for a single relativistic round trip for even a modest crewed vessel exceeds the output of entire stellar systems. Relativistic travel also creates hazards that have no counterpart at lower speeds. At 90% of light speed, even a single milligram grain of interstellar dust carries the kinetic energy equivalent of the detonation of a large explosive device. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter on average, along with scattered dust grains at much lower densities. At relativistic velocities, these particles strike the forward surface of the spacecraft as a continuous, devastating bombardment. The shielding required to protect the crew from this flux would be enormous, adding mass, which increases the energy required for acceleration, which compounds every other problem in the chain. Every pathway to the stars leads to the same convergence. The distances are real, the physics is what it is, the energy requirements are civilization scale or beyond, and every solution that addresses one constraint creates new versions of the others. Chemical rockets are too slow by a factor of thousands. Nuclear rockets are too slow by a factor of hundreds. Fusion rockets might reduce the journey to a human lifetime, but impose radiation reliability and life support demands that remain unsolved. Laser sails can reach the required speeds, but only for payloads measured in grams, not the thousands of tons required to keep a crew alive. Generation ships require closed ecosystems and stable societies sustained for centuries, neither of which humanity has demonstrated. Suspended animation does not exist. Relativistic travel requires energy inputs that exceed the output of the sun. The nearest star is not merely far, it is far in a way that resists every strategy human ingenuity has yet conceived. And the strategy that has not yet been conceived cannot be assumed to exist. The human body did not evolve for space. This statement sounds obvious. It is obvious. And yet, its full implications are consistently underestimated in discussions of long-duration space travel, treated as a collection of engineering problems, awaiting engineering solutions, rather than as a set of biological facts about what a human organism fundamentally is and what it requires to continue functioning. The distinction matters enormously because engineering problems have engineering solutions, while biological facts simply are what they are. Decades of human spaceflight research have produced a picture of what extended time in the space environment does to the human body. That picture is not encouraging. It is not a list of manageable inconveniences that better technology will eliminate. It is a catalogue of documented, measured, peer-reviewed damage that accumulates in multiple organ systems simultaneously, that worsens with time rather than stabilizing, and that in several cases appears to be partially or fully irreversible, even after return to Earth and full gravity and comprehensive medical care. Begin with the skeleton. Bone is not a static material. It is living tissue continuously broken down and rebuilt by specialized cells called osteoclasts, and osteoblasts regulated by a complex system of hormonal signals, mechanical loading, and metabolic feedback. On Earth, gravity provides constant mechanical stress to the skeleton, particularly to weight-bearing bones such as the hips, pelvis, spine, and legs. That stress is the signal that tells the body to maintain bone density. Remove the stress. As spaceflight does and the signal weakens, the osteoclasts continue breaking down old bone. The osteoblasts slow their rebuilding. The net result is bone loss at a rate of approximately 1 to 2% per month, concentrated in precisely the bones that bear the greatest loads on Earth. On the International Space Station, astronauts exercise for 2 hours every day using specialized resistance machines that attempt to simulate the mechanical loading gravity provides. The Advanced Resistive Exercise Device generates forces of up to 600 pounds, allowing astronauts to perform squats, deadlifts, and other resistance exercises in microgravity. This aggressive countermeasure protocol represents the best current approach to preserving bone density in space. Even with it, astronauts returning from 6-month missions show measurable reductions in bone mineral density that require between 12 and 18 months of recovery on Earth to partially reverse. Partially, not fully. Several studies of long-duration astronauts have found that recovery plateaus before full restoration of pre-flight bone density. A portion of the bone lost during spaceflight does not return even after years back on Earth with full gravity and comprehensive rehabilitation. The skeleton that a person carries back from a long space mission is not the same skeleton they carried aboard. It is measurably weaker in specific regions, and that weakness appears to be permanent. On a mission of months, this is a manageable consequence. The astronaut returns, undergoes rehabilitation, recovers most of what was lost, and continues their life with a modestly elevated fracture risk in specific bones. On a mission of years or decades, the accumulated bone loss would far exceed anything observed in current astronauts. An astronaut on a 3-year Mars mission would experience bone loss across the entire transit and surface stay, partially offset by the 38% gravity on Mars during the surface phase, but exposed to full microgravity during both 7-month transit legs. The cumulative deficit would be severe. A fracture during this mission of a hip or vertebra weakened by years of density loss would transform from a medical event into a potential mission-ending emergency with no adequate treatment options available. Muscle follows the same trajectory. Without the constant resistance of gravity, skeletal muscles lose mass and strength at rates that exercise can slow but not prevent. Fast-twitch muscle fibers, which provide explosive force and rapid response, atrophy particularly quickly. Slow-twitch fibers, which provide endurance, fare somewhat better, but still decline. The cardiac muscle is also affected. The heart, which on Earth works continuously against the downward pull of gravity to circulate blood throughout the body, remodels in microgravity. It becomes more spherical, losing some of the efficient, elongated geometry that makes it effective as a pump. Studies of returning astronauts have documented changes in cardiac structure and function, including reduced stroke volume and altered ejection fraction that persist for months after return to Earth. On a mission with no return to Earth for years, these cardiovascular changes would progress without interruption. The crew would be performing critical technical tasks, conducting scientific work, making decisions under pressure, and potentially performing emergency repairs with hearts and muscles that had been continuously degrading for months, years. The physiological baseline they were operating from would be meaningfully worse than what they started with, and it would continue to worsen throughout the mission. Vision impairment has emerged as one of the more alarming and unexpected consequences of long-duration spaceflight. The condition, now designated spaceflight-associated neuroocular syndrome, affects a significant fraction of astronauts on extended missions and produces changes that were not anticipated when long-duration spaceflight programs began. The syndrome involves flattening of the back of the eyeball, swelling of the optic nerve head, development of small folds in the retina, and changes in the flow and pressure of cerebrospinal fluid surrounding the brain and optic nerves. The likely mechanism involves the fluid shift that occurs in microgravity. On Earth, gravity pulls blood and other bodily fluids downward away from the head. In microgravity, this distribution changes. Fluid accumulates in the upper body and head in greater quantities than the body is designed to manage, increasing pressure within the skull and altering the mechanical environment of the optic nerve and the structures of the eye. The effect is subtle and develops gradually, which is part of why it went unrecognized for decades of human spaceflight. Some astronauts have returned from 6-month missions with measurable reductions in visual acuity that had not fully resolved a year after landing. Others have shown structural changes in the optic nerve and retina that appear permanent. No effective countermeasure has been identified. The problem is not yet fully understood at the mechanistic level, which makes designing a solution difficult. On a multi-year mission in deep space, progressive vision impairment could compromise the crew's ability to read instruments, perform precision tasks, conduct repairs requiring fine motor control, and make the visual assessments that mission safety depends on. The immune system weakens in ways that create compounding risks in the confined environment of a spacecraft. Studies have documented reactivation of latent viruses in astronauts during and after spaceflight, including varicella zoster, the virus that causes chickenpox and shingles, and Epstein-Barr, the virus responsible for mononucleosis. These viruses establish permanent residence in the body after initial infection and are held in check by a functioning immune system. When immune surveillance weakens, they reactivate. T-cell function is altered. The immune response to novel pathogens is blunted. Wound healing slows. In a small crew confined in a sealed environment for years, the combination of weakened immune function and close proximity creates conditions favorable for infectious disease. Pathogens circulate efficiently in enclosed spaces. A respiratory virus that would cause a week of discomfort in a person with a healthy immune system on Earth could produce a more serious illness in someone with a compromised immune response. An infected wound that would heal quickly with good immune function and appropriate care might progress to sepsis in a crew member whose immune system has been degraded by months of cosmic radiation exposure and the other stresses of spaceflight. The kidney findings published in June of 2024 by researchers at University College London added a new dimension to the catalogue of spaceflight-related physiological damage. The study found that exposure to galactic cosmic radiation and microgravity causes structural and functional changes in kidney tissue at a level beyond what had previously been understood. The research identified damage to the tubular structures within the kidney responsible for filtering waste and regulating fluid balance, changes that could impair kidney function progressively over the course of a long mission. Kidney stones are already a recognized risk in long-duration spaceflight. Bone demineralization releases calcium into the bloodstream, which concentrates in the urine and promotes stone formation. Dehydration, a persistent challenge in spacecraft water management, increases the risk further. The 2024 findings suggest the problem is more fundamental than calcium management alone, involving tissue-level changes in the kidney's filtering structures that develop in response to radiation exposure and microgravity, independently of hydration status. On Earth, a kidney stone is painful and disruptive but treatable. Depending on the size and location, it may pass on its own or require medical intervention. A crew member in deep space who develops a kidney stone faces a different situation entirely. If the stone becomes obstructed and infection develops in the kidney, the resulting sepsis is a life-threatening condition requiring aggressive medical intervention. The crew has no surgeon aboard trained in urological procedures. They have limited imaging capability to assess the severity of the obstruction. They have a finite supply of antibiotics that cannot be replenished, and they have no option to evacuate the patient to a higher level of care. The central nervous system effects of galactic cosmic radiation deserve particular attention because they represent the category of damage with the least understood long-term consequences and the most concerning implications for crew function over extended missions. Heavy ion particles, the HZE particles produced by supernovae and other violent astrophysical events, are uniquely damaging to neural tissue. They do not merely increase the statistical risk of cancer in the brain. They directly disrupt neural circuits, damage synaptic connections, and alter the signaling pathways that govern cognition, memory, and emotional regulation. Animal studies using simulated cosmic radiation environments have produced results that give pause. Rodents exposed to HZE particle fluxes, similar to what a crew would experience during an interplanetary transit, showed measurable declines in performance on tasks requiring learning, memory, and decision-making. The changes appeared months after the radiation exposure, not immediately suggesting that the damage accumulates and manifests gradually rather than producing acute effects. The cognitive domains most affected included the executive functions, the higher-order mental processes that govern planning, problem-solving, and response to novel situations, precisely the functions that a crew must rely on most heavily during an emergency. Translating animal studies to human predictions requires caution, but the underlying biology is not species-specific. The neural structures affected by HZE particles in rodents are homologous to those in humans. The mechanisms of damage are physical and chemical, not dependent on species-specific biology, in ways that would make humans uniquely immune. The question is not whether HZE radiation damages human neural tissue, but how much damage accumulates at interplanetary flux levels across mission durations of years, and what the functional consequences of that damage are for the crew. We do not have that data yet because no human being has ever been exposed to those fluxes for those durations. The astronauts on the International Space Station are partially protected by Earth's magnetic field, which deflects a significant fraction of the cosmic ray flux that a crew in interplanetary space would receive unimpeded. The data from station missions, while valuable, does not characterize the deep space radiation environment that a Mars crew would inhabit for nearly 3 years. NASA is aware of this gap. The agency's Human Research Program has been studying the physiological effects of spaceflight for decades, and its researchers have been candid about the uncertainties that remain. A 2023 report from the program identified 22 distinct human research risks associated with long-duration spaceflight beyond Earth's orbit, ranging from the well-characterized bone and muscle effects, less understood risks involving behavioral health, sensoromotor, adaptation, and the long-term consequences of cosmic radiation exposure. The report noted that several of these risks remain at the level of insufficient evidence, meaning that the data needed to properly quantify and manage them does not yet exist. This is not a criticism of NASA's research program. It is an honest statement about what long-duration deep space travel would require us to know before we could claim to understand the risks we were asking a crew to accept. Sending people to Mars before that evidence exists means sending them into an incompletely characterized risk environment, asking them to accept consequences that we cannot fully predict and cannot intervene to address once they develop. The psychological dimension of long-duration spaceflight adds a layer of complexity that physiological measures alone do not capture. Human beings are social animals in the most fundamental biological sense. The need for social connection, for varied and novel stimulation, for a sense of meaningful agency over one's environment and future is not a preference or a personality trait. It is a basic requirement of psychological health, as fundamental as the requirements for food and water. Remove it for long enough, and the consequences are measurable in the same way that bone loss is measurable. Cognitive function declines, emotional regulation deteriorates, interpersonal conflict escalates, motivation erodes. The Mars 500 experiment conducted in Moscow between 2010 and 2011 confined 6 volunteers in a simulated spacecraft environment for 520 days, the approximate duration of a Mars mission. The experiment was designed to characterize the psychological effects of the isolation and confinement that a real mission would impose. The results documented significant deterioration in multiple domains. Several participants showed marked increases in sedentary behavior across the experiment's duration, spending more time lying down and less time in active tasks. Sleep quality declined for most participants. Cognitive performance on standardized tests decreased. The crew showed signs of what researchers described as psychological hibernation, a withdrawal from engagement that served as a coping mechanism against an environment that provided insufficient stimulation to sustain normal, motivational levels. And the participants knew they were on Earth. They knew that in a genuine emergency, someone would open the door. They knew that the experiment would end. They knew that their families were minutes away rather than months. The psychological safety net that this knowledge provided is not available to a crew genuinely en route to Mars. The awareness that the door does not open, that the experiment does not end early, that Earth is retreating at thousands of miles per hour and will not be within any meaningful reach for years, imposes a psychological pressure that no Earth-based simulation can fully replicate. Select the crew poorly, and the interpersonal dynamics of a small group confined in close quarters for years become a mission risk, as serious as any hardware failure. Select the crew well, and the pressure still accumulates. The research literature on isolated and confined environments, including Antarctic winter overstations, submarine deployments, and spaceflight analog missions, consistently shows that even well-selected, highly trained individuals in supportive group dynamics experience significant psychological strain across extended periods of confinement. The strain is not a character flaw. It is a response to conditions that human psychology was not designed to endure. Communication with Earth, which one might expect to provide psychological support, becomes a source of its own complications at interplanetary distances. A message sent to Earth from Mars arrives at minimum 4 minutes later, and the reply arrives 4 minutes after that. A conversation becomes an exchange of monologues separated by waiting periods long enough to break the natural rhythm of dialogue. Mission controllers can provide technical guidance, emotional support, and information about events on Earth, but they cannot provide the real-time responsiveness that makes human communication feel like connection rather than correspondence. As the mission progresses and Earth recedes, the communication delay grows. The crew adapts because adaptation is what humans do, but adaptation to isolation is not the same as thriving within it. The crew that arrives at Mars after 7 months of transit will not be psychologically identical to the crew that departed Earth. They will be changed by the transit in ways that are difficult to predict and impossible to reverse during the mission. These physiological and psychological realities collectively define a hard limit on long-duration human spaceflight that is often spoken of as a set of problems awaiting solutions, but that functions in practice as a boundary. Not a boundary drawn by engineering, but one drawn by biology, by what the human organism is, what it requires, and what happens to it when those requirements go partially or fully unmet for months or years. The boundary is not fixed at a single distance or duration. It shifts depending on which technologies are available to mitigate specific risks. Better radiation shielding pushes it outward. More effective bone loss countermeasures push it outward. Improved closed-loop life support, better psychological support systems, more effective medical capabilities aboard the spacecraft all push it outward somewhat, but they do not dissolve it, they move it. And the distances involved in interstellar travel are so vast that moving the boundary by factors of 2 or 5 or even 10 still leaves it nowhere near the nearest star. A Mars mission, the nearest and most forgiving interplanetary target, already operates at the outer edge of what the documented physiological and psychological effects of spaceflight suggest is survivable within current medical and technological frameworks. The cumulative radiation dose approaches career limits. The bone and muscle loss across 3 years in partial and zero gravity would be the most severe ever experienced by any human crew. The psychological isolation would be unprecedented in duration. The medical autonomy demanded would require crew members to make decisions and perform procedures that lie at the outer edge of what any training program can adequately prepare them for. Every destination beyond Mars imposes these same stresses for longer durations. Longer transit times mean more bone loss, more muscle atrophy, more radiation exposure, more psychological strain, more time for medical emergencies to develop, and fewer resources to address them. The physiological problems that are managed with difficulty at Mars become unmanageable at Jupiter and effectively incompatible with survival at Saturn and beyond. This is the honest reading of the evidence, not pessimism, not a failure of imagination. An honest reading of what decades of human spaceflight research has documented about what space does to human biology applied to the distances and durations that the solar system and beyond would demand. The machines we send into the deep solar system and beyond do not face any of these constraints. They do not lose bone. They do not develop kidney stones. They do not experience depression or interpersonal conflict. They do not require 2 hours of daily exercise to maintain the minimum physical function needed to perform their tasks. They can be designed to tolerate radiation levels that would kill a human crew within hours, built from materials chosen specifically for their radiation resistance, with redundant systems that compensate for component failures without human intervention. The gap between what a robotic probe can endure and what a human crew can survive is not a gap that will be closed by incremental improvements in either direction. It is a structural feature of the difference between machines and biology, between systems that can be engineered for specific environments and organisms that evolved for a specific environment and cannot be re-engineered from the ground up. However sophisticated our medical and technological capabilities become. Understanding this gap honestly without flinching from what it implies is the prerequisite for answering the original question with accuracy rather than comfort. And the answer it points toward is both more constrained than most people believe and more remarkable than the constraint might initially suggest. What remains is to define precisely where the human frontier ends, what that boundary means for our species, and what lies on the other side of it that human eyes will never see, but human instruments might yet describe. Every journey discussed so far leads to the same intersection. Not a wall, not a single barrier erected at a specific distance from Earth. An intersection, a point in the progression from near to far, where 4 distinct constraints converge simultaneously, where each one alone might be manageable, but together they form a boundary as absolute as any law of physics. Those 4 constraints are speed, time, survival, and energy. And understanding how they interact is the key to understanding where the human frontier actually ends. Speed determines how long a journey takes. Time determines what the human body and the spacecraft must endure during that journey. Survival determines the mass and complexity of the systems required to keep the crew alive across that duration. Energy determines whether the total mission is physically achievable given the resources available to a civilization. Each constraint feeds into the others in ways that compound rather than add. Fix one and you worsen another. Increase speed and the energy required escalates by exponential factors. Extend duration and the survival requirements multiply beyond what any demonstrated closed system can sustain. Add shielding to manage radiation and you increase mass, which demands more energy, which demands more fuel, which demands a larger vehicle, which demands more shielding. The feedback loops do not cancel, they amplify. At close range within the Earth-Moon system, all 4 constraints are satisfied without extraordinary difficulty. Speed is adequate at current rocket velocities. Time is short enough that human biology is not pushed beyond manageable limits. Survival is achievable with technologies that exist and have been demonstrated. Energy is within the reach of launch systems that humanity currently operates. The moon is hard. The moon demands engineering of the highest order and courage, of a kind that very few people will ever be called upon to demonstrate. But the moon is within the intersection where all 4 constraints can be satisfied simultaneously. At Mars, the constraints tighten dramatically, but remain within the plausible reach of technology that could exist within this century. The transit time is long but not incompatible with human survival given adequate countermeasures. The radiation dose is severe but potentially manageable, with improved shielding and mission design. The closed-loop life support requirement is demanding but not demonstrably impossible for 3 years. The energy requirement is enormous, but not beyond what advanced launch systems could theoretically provide. Mars sits at the outer edge of the zone, where the 4 constraints overlap the zone, where a crewed mission is extraordinarily difficult but not physically impossible. Beyond Mars, the constraints begin to overpower each other. The overlap zone shrinks. The region where all 4 can be simultaneously satisfied narrows towards 0, and at some distance, at some combination of speed and duration and mass and energy, the overlap disappears entirely. The 4 constraints no longer intersect in a space that admits a solution. There is no narration of propulsion system, life support, shielding, and mission profile that satisfies all four at once. The mission becomes not merely difficult but physically incoherent. Where is that point? Consider what the most optimistic, honest scenario looks like. Not science fiction, not physics violations. The most generous extrapolation from known science and plausible technological development that intellectual honesty permits. Assume nuclear fusion propulsion works. Assume engineers solve the controlled fusion problem, miniaturize the reactor to spacecraft scale, and develop an engine that produces exhaust velocities of several thousand kilometers per second, enabling a spacecraft to reach approximately 5% of the speed of light. This is an enormous assumption. Fusion power has not been demonstrated as a practical energy source after 7 decades of intensive research, but it does not violate known physics. It is conceivable in principle. Assume closed-loop life support functions reliably for 20 to 30 years. Assume engineers solve the ecological stability problems that have defeated every previous attempt, developing systems that maintain atmospheric composition, water quality, and food production without external intervention across decades of operation. Again, an enormous assumption with no demonstrated precedent, but not a physics violation. Assume radiation shielding sufficient to keep cumulative crew exposure below career limits over a 20 to 30-year mission. Assume artificial gravity through spacecraft rotation eliminates the bone loss, muscle atrophy, and cardiovascular deconditioning that currently limit long-duration spaceflight. Assume a crew selected and prepared to withstand years of isolation with minimal psychological deterioration. Assume a civilization willing and able to dedicate the resources required to design, build, and operate such a mission across the decades, from initial concept to final return. Under every one of these assumptions extended far beyond what current evidence supports. What is the farthest a human crew could travel and return from within a time frame compatible with human biology? A fusion-powered spacecraft achieving 5% of the speed of light covers roughly 15000 kilometers per second. At that velocity, it travels 1 light-year in approximately 20 years. The nearest star at 4.24 light-years would require roughly 85 years of transit each way. A round trip without any time at the destination would last 170 years. That exceeds not just a human lifespan but the demonstrated operational lifetime of any complex engineered system by a factor of several. Reduce the ambition. A one-way journey of 20 years would reach approximately 1 light-year from Earth. A round-trip mission of 20 years, total 10 years each way with no time at the destination, would reach half a light-year. A round trip of 12 years allowing 2 years at the destination would cover a maximum of approximately a quarter of a light-year in each direction. A quarter of a light-year. Expressed in astronomical units, that is roughly 16000. Expressed in miles, it is approximately 1.5 trillion. That is the approximate range at which the most optimistic crewed mission using technology that does not yet exist but does not violate physics could travel and return within a time frame that human biology and life support endurance could conceivably accommodate. It is a distance that dwarfs everything humanity has ever achieved in space by an almost incomprehensible margin. Voyager 1, after nearly 50 years of flight, sits at approximately 172 astronomical units. A quarter of a light-year is 16000 astronomical units. The most optimistic human journey would reach nearly 100 times farther than our most distant probe has traveled in half a century of continuous flight. It would place a crew well into the inner reaches of the Oort cloud, the vast shell of frozen bodies that marks the outermost gravitational domain of the Sun. They would be surrounded by comets and icy debris drifting in orbits so slow and so vast that they complete a single revolution around the Sun in millions of years. The nearest other star would still be 3/4 of the distance away that it was when the crew departed Earth. And they would not reach it. This is the honest answer. Not the answer that science fiction prefers. Not the answer that optimistic timelines imply. The answer that the intersection of speed, time, survival, and energy produces when you follow the mathematics wherever it leads. The maximum plausible range of human space travel under the most generous assumptions that intellectual honesty allows is approximately a quarter of a light year, perhaps somewhat more if fusion propulsion significantly outperforms current projections, perhaps somewhat less if the biological and life support challenges prove harder to solve than assumed. The uncertainty in the estimate is real, but its center of gravity is clear. Somewhere in the dark space between the outer solar system and the inner reaches of the Oort cloud, the human frontier ends. Now place that frontier in context, not the context of human achievement where it represents an extraordinary expansion of our reach. The context of the universe itself, where the only context that gives the number its true meaning. The Milky Way galaxy spans approximately 1,000,000 light years from edge to edge. A quarter of a light year is 1/400th of that diameter. If the Milky Way were compressed to the size of the continental United States, the maximum range of human travel would be approximately the width of a single human hair. Not a city block, not a room, a hair. The observable universe contains an estimated 2 trillion galaxies, distributed across a volume roughly 93 billion light-years in diameter. The ratio of the maximum human journey to the diameter of the observable universe is approximately 3 trillionths. Written as a decimal, it is 0.0000000000003. In scientific notation, 3 times 10 to the power of -12. There is no everyday analogy that captures a number this small without itself becoming an exercise in the failure of human intuition to process scale. Try anyway. If you filled a sphere the size of Earth with grains of fine sand, each grain representing the maximum human journey of a quarter of a light year, the total number of grains would still be far smaller than the number needed to represent the diameter of the observable universe in the same units. The human frontier is not a rounding error in the cosmic ledger. It is smaller than a rounding error. It is smaller than the uncertainty in a rounding error. This is not a failure unique to humanity. It is a statement about the universe's architecture. The distances between stars were not set by any consideration of biological travelers. They were set by the physics of stellar formation, by the gravitational dynamics of gas clouds collapsing under their own weight, by the balance between radiation pressure pushing outward and gravity pulling inward, by processes that operate on timescales of millions of years and care nothing for the metabolic requirements of carbon-based organisms with 70-year lifespans. The nearest star to the Sun is 4.24 light-years away, not because the universe placed it at a convenient distance, but because the density of matter in the galactic disk and the physics of star formation produce average stellar separations of several light-years in this region of the Milky Way. The universe did not consult biology when it arranged itself, and biology did not consult the universe when it arranged itself. Evolution produced organisms optimized for survival and reproduction in the specific environment of Earth's surface. It produced creatures that require specific temperatures, specific atmospheric compositions, specific gravitational conditions, specific inputs of water and organic chemistry at regular intervals. It produced creatures with lifespans measured in decades rather than centuries, with immune systems calibrated for Earth's pathogens rather than the radiation environment of interstellar space, with psychological architectures that require social connection and varied stimulation in quantities that deep space travel cannot provide. The mismatch between what biology requires and what the universe offers beyond Earth's immediate neighborhood is not a temporary condition awaiting a technological fix. It is a fundamental feature of the relationship between the scale of the cosmos and the scale of biological life. Stars are separated by light years. Biological organisms live for decades. The ratio between those two quantities is approximately 10,000 to 1 in favor of the universe, and no amount of engineering reduces that ratio to 1. What engineering can do, and what it has done with extraordinary success, is extend the reach of human instruments, human curiosity, and human knowledge far beyond the reach of human bodies. This distinction is the most important one in understanding what humanity's actual relationship with the universe looks like, as opposed to what we wish it looked like. Robotic probes have visited every planet in the solar system. Voyager 2 flew past Jupiter, Saturn, Uranus, and Neptune between 1979 and 1989, completing its grand tour in 12 years. The Cassini spacecraft orbited Saturn for 13 years from 2004 to 2017, returning data that reshaped understanding of the ringed planet and its moons. New Horizons flew past Pluto in 2015 after a 9.5-year journey, revealing a geologically active world that defied expectations. The James Webb Space Telescope, operating at a distance of roughly 1 million miles from Earth, is detecting light from galaxies that formed within the first few 100 million years after the Big Bang light that has been traveling for more than 13 billion years before reaching Webb's Mirosh. Every one of these missions extended human knowledge to distances and scales that human bodies will never reach, and every one of them was accomplished by machines that did not eat, did not breathe, did not develop bone loss or kidney stones or vision impairment, did not require psychological support or exercise equipment or medical care, and did not experience the 22 distinct human research risks that NASA's Human Research Program has identified as challenges for long-duration crewed spaceflight. The Hubble Space Telescope, launched in 1990 and still operational more than 3 decades later, has observed galaxies at distances exceeding 13 billion light-years. In a single deep field image, a patch of sky smaller than a grain of sand held at arm's length, Hubble captured roughly 10,000 galaxies, each containing hundreds of billions of stars, each potentially hosting planetary systems of its own. The information in that image represents a reach into the universe so vast that expressing it in any unit relatable to human experience requires numbers that the human brain was not designed to process intuitively. Human eyes looked at those images. Human minds interpreted them. Human curiosity drove the design, launch, and operation of the telescope that captured them. In this sense, humanity has already reached 13 billion light-years into the universe. Not with our bodies. With our instruments, our mathematics, our insatiable need to know what is out there, beyond what we can directly see or touch. This is the asymmetry that defines humanity's actual relationship with the cosmos. We are a species that can see 13 billion light-years, but travel a fraction of a light-year. We can detect the composition of the atmosphere of a planet orbiting a star of 40 light-years away by analyzing the light that filters through it during a transit, but we cannot send a human being to that star within any time frame that preserves the biological continuity of the traveler. We can measure the mass of a black hole 1 billion light-years away through gravitational wave astronomy, but we cannot place a crew outside the solar system. Our eyes outrun our hands by a factor of trillions. Our hands outrun our feet by a factor that grows with every kilometer of interplanetary space we attempt to cross. The hierarchy is absolute, and the ratios are vast. Seeing, then reaching, then traveling in that order, with each step separated from the next by a gap so large that no linear progress in technology closes it. The radio signals generated by human civilization since the invention of high-power broadcasting in the 1930s and 1940s have been expanding outward at the speed of light for nearly a century. That sphere of electromagnetic radiation, the accidental announcement of humanity's existence to the galaxy, currently extends approximately 90 light-years in radius. Within that sphere sit roughly 1,000,000 stars. If any civilization orbiting one of those stars possesses sufficiently sensitive receivers and has been pointing them in our direction, they may have already detected the electromagnetic fingerprint of human civilization. Our signals travel at the speed of light. Our signals are already 90 light-years into the galaxy. Our bodies have reached 172 astronomical units, less than 1/2% of a single light-year. The signals will continue expanding. By the time any human crew, under the most optimistic possible assumptions, reaches 1/4 of a light-year from Earth, the electromagnetic sphere, announcing human existence, will have expanded to more than 100 light-years in radius, reaching tens of thousands of stars. Our presence in the galaxy, as measured by the extent of our electromagnetic influence, already vastly exceeds our physical reach. It will continue. This is perhaps the most honest portrait of what humanity is in the universe. Not a species on the verge of conquering the stars, not a civilization whose physical reach will eventually match its intellectual ambitions. A species of remarkable, unprecedented, and genuinely extraordinary reach in the domains of knowledge, signal, and instrument confined to a physical range so small relative to the cosmos that it does not register on any map drawn at galactic scale. The Artemis 2 crew traveled 252,000 miles and broke a record that had stood for 56 years. That journey, the greatest physical reach any human being has ever achieved, represents a distance that light covers in 1.3 seconds, one heartbeat, one breath. In the currency of the cosmos, the farthest humans have ever traveled does not produce a number worth writing down. And yet they went, and yet we watched, and yet the moment meant something not because of the distance, but because of what the distance cost and what it proved about the species that paid that cost. The tyranny of the rocket equation, first described mathematically by Konstantin Tsiolkovsky in 1897, has governed every crewed mission in the history of spaceflight and will govern every crewed mission in the foreseeable future. The equation states that the velocity achievable by a rocket is determined by the exhaust velocity of its propellant and the logarithm of the ratio of the rocket's initial mass to its final mass. The logarithmic relationship is the source of the tyranny. To go twice as fast does not require twice as much fuel. It requires exponentially more. To go 10 times as fast requires not 10 times the fuel, but hundreds or thousands of times more, depending on the specific exhaust velocity of the propulsion system. This relationship does not change with engineering progress. It is not a limitation of current technology waiting to be overcome by better technology. It is a mathematical feature of the relationship between kinetic energy and mass that applies to any propulsion system that works by expelling mass. Chemical rockets, nuclear thermal rockets, nuclear electric systems, fusion drives, all are subject to the tyranny of the rocket equation in forms that vary in severity but not in fundamental character. Only propulsion systems that do not expel mass from the spacecraft, such as laser sails pushed by external photon pressure, escape the equation entirely. And those systems, as the breakthrough Starshot experience demonstrated, face a different set of engineering challenges so severe that they have defeated sustained efforts by world-class teams with significant funding. The resource ceiling that these constraints impose is not theoretical, it is practical and near. A crewed Mars mission would consume a significant fraction of any major space agency's budget for decades. A crewed Jupiter mission, if one were ever seriously proposed, would require resources on the scale of a major national economy sustained over decades of preparation and execution. A crewed interstellar mission, even to the nearest star, would require the focused output of an entire planetary civilization sustained over centuries across political upheavals, economic crises, technological revolutions, and the ordinary entropy that dissolves human institutions across long timescales. No human institution has ever maintained a single engineering project for centuries. The longest continuously operating human institutions, certain universities and religious organizations, have maintained organizational continuity for centuries, but have not sustained a single specific technical project across that nice span. The Manhattan Project lasted 6 years. The Apollo program lasted 12. The International Space Station, the longest continuous human space project in history, has operated for 25 years and has required the sustained cooperation of 15 nations throughout. A crewed interstellar mission would need to sustain that level of commitment for 10 or 50 or 100 times longer across changes of government, changes of scientific priority, economic depressions, wars, and the gradual cultural shifts that make the concerns of one generation unrecognizable to generations several centuries removed. The practical upper limit of human space travel is therefore determined not only by physics and biology, but by the nature of human civilization itself. Even if the physics permitted a crew to survive an 85-year journey to Proxima Centauri, The social, economic, and political structures required to execute such a mission might exceed what human societies are capable of maintaining. This is not a criticism. It is an observation about the kind of species we are, the kind of projects we can sustain, and the kind of universe we find ourselves in. There is a strange beauty in arriving at a limit. Not the beauty of triumph, not the beauty of a summit reached or a record broken or a destination finally touched after years of striving toward it. A different kind of beauty, the beauty of honest reckoning, the beauty that comes from looking at something clearly without softening its edges or adjusting its proportions to fit what you wished were true, and finding that the truth itself, unadorned and exact, contains something worth holding. The question was simple. How far could humans ever actually travel in space? Not in science fiction, not in the optimistic timelines of space agencies announcing missions a decade away that quietly become 2 decades away, and then 3. Not in the dreams that have animated human imaginations since the first person looked up at a dark sky and felt the pull of what lay beyond. In reality, in the universe, as physics has described it, as biology has constrained it, and as the arithmetic of energy and mass and time has bounded it with a precision that desire cannot alter, the answer arrived not as a single number but as an intersection, 4 curves meeting at a point where ambition stops and physics speaks. Speed limited by the energy available to any propulsion system that does not violate known science. Time limited by the biological lifespan of a human crew and the mechanical endurance of any system complex enough to sustain them. Survival limited by what radiation does to human tissue, what microgravity does to human bone and muscle and vision and kidney function, what isolation does to human psychology across years of confinement in a sealed metal environment. Energy limited by the fuel mass that can be launched from a planetary surface, the efficiency of any propulsion system yet conceived, and the total resources that a civilization can dedicate to a single mission sustained across decades. Where those 4 curves cross the human frontier ends. That crossing point arrived at under the most generous assumptions that intellectual honesty permits, sits at approximately 1/4 of a light year from Earth. Perhaps somewhat more if fusion propulsion significantly outperforms current projections and if the biological challenges of long-duration spaceflight prove more tractable than the evidence currently suggests. Perhaps somewhat less if they prove harder. But the center of gravity of the estimate is clear. Somewhere in the dark, cold space between the outermost planets and the inner reaches of the Oort cloud human physical presence in the universe reaches its limit, 1/4 of a light year, 16,000 astronomical units, roughly 1.5 trillion miles. It is a distance that no human being has come remotely close to traveling. It is a distance that exceeds Voyager 1's 50-year journey by a factor of nearly 100. It is a distance so far beyond anything our species has achieved that calling it a limit feels almost generous given where we currently stand. The farthest human being in history traveled 252,000 miles. The limit is approximately 6 billion times farther than that, and yet measured against the universe, it is nothing. The Milky Way is 1,000,000 light years across. 1/4 of a light year is 1/400th of that diameter. The observable universe spans 93 billion light years. The ratio of the maximum human journey to the diameter of the observable universe is 3 trillionths, not 3%, not 3,000ths of a percent, 3 trillionths. A number so small that every analogy constructed to illustrate it undershoots the reality. Consider one final attempt. Imagine the observable universe compressed to the size of Earth. Every galaxy, every filament of dark matter, every void and supercluster, all of it scaled down until the entire observable cosmos fits within a sphere 8,000 miles across. At that scale, the Milky Way would be roughly the size of a bacterium invisible to the naked eye, detectable only under significant magnification. The maximum range of human travel would be smaller than a single atom within that bacterium. This is not exaggeration, this is arithmetic. Sit with that for a moment, not as a source of despair, but as an invitation to understand something true about the universe, and something true about the species, contemplating it from a small rocky world, orbiting an unremarkable star in the outer reaches of one galaxy. Among 2 trillion, the universe is not hostile to human beings. It is not designed to exclude us, to humble us, to remind us of our insignificance. It is simply vast in a way that has nothing to do with us. The distances between stars were set by stellar physics before the first carbon atom was incorporated into the first self-replicating molecule on Earth. The speed of light was a feature of the universe for 13.8 billion years before any biological organism evolved the neural complexity to measure it. The radiation environment of interstellar space was present and indifferent for billions of years before any creature developed the cognitive capacity to understand what radiation is or what it does to the cells it passes through. The universe did not build walls to keep us in. It built a cosmos at the scale appropriate to its own physics, and we evolved at the scale appropriate to the chemistry of a planetary surface. The mismatch between those 2 scales is the fundamental condition of human existence in the universe. We are creatures of a particular size, a particular lifespan, a particular set of biological requirements, contemplating a cosmos built at scales that exceed our physical reach by factors that resist comprehension. And yet we comprehend them. This is the fact that the limit cannot diminish the fact that sits at the center of everything this journey has examined. A species that cannot travel more than 1/4 of a light year has nevertheless measured the distance to the edge of the observable universe. A species confined to one planetary system has detected the gravitational waves produced by black holes colliding 1 billion light-years away. A species whose most distant emissary has traveled 172 astronomical units in 50 years has identified thousands of planets orbiting other stars, characterized their sizes and orbital periods, and in some cases, their atmospheric compositions from the surface of the world. It has never left in any meaningful sense. Human knowledge has already crossed every frontier that human bodies cannot. The James Webb Space Telescope observes galaxies whose light left them when the universe was less than 500 million years old. The Event Horizon Telescope produced an image of the shadow of a black hole 6.5 billion times the mass of the Sun, located 55 million light-years away in the galaxy Messier 87. Gravitational wave observatories have detected the merger of neutron stars and black holes across distances so vast that the events occurred before Earth existed. The Voyager spacecraft, traveling at 3,800 miles per hour for nearly 50 years, has returned data from interstellar space. And human minds, sitting on the surface of a world they cannot leave in any cosmic sense, have interpreted that data and understood what it means. The gap between what we know and where we can go is the most extraordinary fact about our species. Every other animal that has ever existed on Earth has been confined to the biosphere, to the thin layer of water and air and soil within which biological life is possible. Every other animal has navigated its world using only the information available within that layer through direct sensory experience of its immediate environment. Humanity alone has developed the cognitive and technological capacity to extend its knowledge far beyond the boundaries of its physical reach, to gather information about realms it cannot enter, to build models of processes it cannot observe, directly and test those models against measurements of extraordinary precision. We are the only thing in the known universe that looks at the universe and tries to understand it. Whether any other such thing exists anywhere in the 2 trillion galaxies of the observable cosmos is the question that the search for extraterrestrial intelligence has been attempting to answer for decades without a confirmed positive end result. But within the portion of the universe that we can examine with current instruments, we are alone in this particular capacity. Alone in our awareness of the cosmos, alone in our attempts to measure it, model it, and understand the laws that govern it. That aloneness is not comfortable, but it is astonishing. The Artemis 2 crew broke a record that had stood for 56 years. Commander Reed Wiseman spoke across the communication link as Orion swept past the moon, and his words carried the weight of every generation that had looked up at the night sky and felt the pull of what lay beyond it. He challenged the explorers who would follow to ensure the record would not stand for long. He was right to do so. Records exist to be broken, and the record of human physical reach into the universe should be broken as often as engineering courage and resources allow. But the record, however far it advances, will advance within a domain whose outer boundary is already visible from where we stand. The physics is not waiting for better technology to reveal a different answer. The answer is what it is. The boundary is where it is. And accepting that honestly without flinching from the scale of the limitation it describes is not the end of the story, it is the frame around the story. And inside that frame, everything humanity has ever done and will ever do takes place within a volume of space so small that it cannot be seen on any map drawn at the scale of the galaxy. That smallness is real, and it makes everything within it more remarkable, not less. Think of what it means for a biological organism assembled from the same atoms forged in stellar interiors, governed by the same physical laws that govern the motion of galaxies, to develop the capacity to look outward and recognize those laws operating at every scale from the subatomic to the cosmological. Think of what it means to be made of the universe and to turn around and study the thing that made you. To measure the distance to Proxima Centauri with enough precision to know that it is 4.24 light-years away and not 4.25. To detect the faint dimming of a distant star's light as a planet crosses its face and infer from that dimming the planet's size, orbital period, and potentially the composition of its atmosphere. To reconstruct the history of the universe from the distribution of galaxies and the spectrum of the cosmic microwave background, light left over from an epoch 380000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and the cosmos became transparent for the first time. None of this required leaving the solar system. None of it required crude missions to the outer planets or robotic probes to neighboring stars. All of it was accomplished from the surface of one world or from instruments placed in orbit around it. The reach of human knowledge is not limited by the reach of human bodies. It never has been. Galileo understood the moons of Jupiter from a garden in Padua. Edwin Hubble understood the expansion of the universe from an observatory on a California mountaintop. The understanding traveled as far as the light that carried the information, and light travels at the speed of light, and the universe is transparent to light across distances that dwarf everything discussed in this journey. The farthest humans could ever travel is a quarter of a light year, perhaps under assumptions so optimistic they require technologies not yet demonstrated. The farthest human knowledge has already reached is the edge of the observable universe, 46.5 billion light-years in every direction, the limit set not by our instruments, but by the finite age of the cosmos and the speed at which light has been able to travel since the beginning of time. The ratio between those two distances is approximately 200 quadrillion to 1. We see 200 quadrillion times farther than we can go. Our instruments outrun our bodies by a factor that has no meaningful analogy in ordinary human experience. And that ratio will grow, not shrink, as technology advances. Future telescopes will see farther. Future detectors will find signals from more distant sources. Future mathematics will extract more information from the data already in hand. Human knowledge of the universe will continue to expand at the speed of light in all directions. For as long as our civilization persists and continues to look outward, human physical presence in the universe will expand too, slowly, painfully, at costs that strain even the most optimistic projections of what our civilization can sustain. From the moon to Mars, perhaps within this century. From Mars to the near asteroids and the moons of Jupiter, through robotic presence, and eventually, if the engineering challenges prove tractable, through human expeditions to the nearest and least hostile of those destinations. From the inner solar system to the outer, through probes of increasing sophistication. From the solar system to the interstellar medium, through the machines we have already sent and the machines we will send in the decades ahead. But the physical presence will always trail the knowledge, always, by margins so vast that no foreseeable change in propulsion technology or biological engineering closes them in any meaningful sense. The frontier of human knowledge and the frontier of human physical reach are not two versions of the same thing advancing at different speeds toward the same destination. They are two fundamentally different kinds of frontier, governed by different physics, subject to different limits, advancing at different rates that diverge rather than converge as the distances involved increase. This is the honest portrait of humanity's place in the universe, not the portrait that popular science prefers with its implicit assumption that the stars are waiting to be reached and that it is only a matter of time and will and engineering ingenuity before human beings stand on worlds orbiting other suns. The honest portrait, a species of extraordinary cognitive reach and modest physical reach, confined to a corner of one galaxy so small it does not register on any cosmic map, capable of understanding the universe in remarkable detail, while remaining unable to visit any but the most immediate fraction of it. The question that began this journey asked how far humans could actually travel. The answer is not a single number pinned to a point in space. It is the place where four constraints intersect. The place where speed and time and survival and energy converge into a boundary that biology cannot cross. That boundary lies closer than most people believe, closer than science fiction suggests, closer than the culture of human space exploration has ever been comfortable admitting. It lies not at the edge of the galaxy, not at the nearest star, not even at the heliopause that Voyager 1 crossed after 50 years of flight. It lies somewhere in the dark and cold between the outermost planets and the inner fringe of the Oort cloud, in a region that most star charts leave blank because there is nothing there to mark. No planets, no moons, no waypoints of any kind. Just distance stretching outward in every direction into a silence that has persisted for billions of years and will persist for billions more. Humanity will send machines past that boundary. We will send signals past it. We will send our curiosity encoded in mathematics and carried on electromagnetic waves deep into a galaxy we will never physically cross. Our instruments will map stars we cannot visit. Our detectors will find planets we cannot walk on. Our telescopes will analyze atmospheres we cannot breathe. We will know the universe in extraordinary and growing detail, while remaining in the most physical sense, confined to a tiny and precious corner of it. That confinement is not a prison. It is not a punishment or a failure or a reason for despair. It is the condition of being the kind of thing that we are in the kind of universe that this is. The same physics that prevents us from crossing interstellar distances is the physics that allows stars to burn planets, to form water, to remain liquid at the surface of a world, and chemistry to produce the staggering complexity of biological life. We are not separate from the laws that limit our range. We are made of them. We are assembled from atoms forged in stellar interiors, governed by forces that operate identically across the observable cosmos, sustained by a star whose energy arrives at the precise wavelengths that our biology evolved to use. We are the universe looking at itself, and the universe looking at itself from inside a biological organism with a 70-year lifespan and a quarter of a light-year of physical reach is still the universe looking at itself. The Artemis 2 crew traveled 252000 miles and felt for a moment the full weight of what that distance cost and what it meant. They were farther from home than any human beings in history, wrapped in the silence of deep space, looking back at an Earth small enough to cover with a thumb. That experience, whatever it does to a person, whatever it permanently rearranges in the architecture of how they understand their own existence, is available to a very small number of human beings and will remain so for the foreseeable future. But the understanding of what lies beyond that distance and beyond the distance, beyond that and beyond the distance, beyond that, reaching outward through the solar system and across the interstellar void and through the local group of galaxies and into the great filaments and voids of large-scale structure of the universe, that understanding is available to anyone who chooses to pursue it. It requires no rocket. It requires no launch window, no launch vehicle, no radiation shielding, no closed-loop life support system, no 3 years of isolation and risk and physical deterioration. It requires only the willingness to look and to follow the numbers wherever they lead and to hold the answers without flinching from what they say. The farthest humans could ever travel is the place where the silence begins, and from that place, looking back at the small bright point of the sun the crew would see what every honest reckoning with the cosmos eventually reveals. Not that humanity is insignificant, but that insignificance and significance are not the same axis. We are small, the universe is large, and a small thing that has learned to measure the large thing is not diminished by the measurement. It is defined by it. The warmth is here, on this world circling this star in this particular moment of cosmic time that will not return. It is brief, it is fragile, it is bounded on every side by distances that our bodies will never cross and our instruments have already reached. It is extraordinary, and it is ours.